All right, we're going to do section 5.5, and there aren't any examples that I'm going to need to write out. It's mostly just reading. So I'm going to read through it, and you can follow along in your book or follow along on mine. But what it says is that these are proofs. We're going to talk about different kinds of proofs. So let's start with a definition. It says a proof is a system of reasoning or an argument to convince a person of the truth of a statement. It says now you will learn various procedures for proving statements, mathematical or otherwise. Before a proof can be meaningful to you, you must question the truth of the statement. You must not accept every statement that you hear as truth without some solid evidence that it is true. So we're going to compare the two main types of reasoning, and that's going to be inductive reasoning and deductive reasoning. So when you're doing inductive, it's defined as an argument to establish that a statement is probably true. It can't be certain, but it's most likely going to be true. I'll give you an example of that pretty soon. And deductive reasoning is an argument to establish that a statement is absolutely certain. So the examples that we're going to look over here are right here. All squares are rectangles. Okay, that's true. And then all rectangles are polygons. That's also true. So that we have a therefore all squares are polygons. So this was a supporting statement. This was a supporting statement. This is a conclusion. We're going to give those special names in a second. Let's take a look at the answer. It says the conclusion is definitely true if the premises are true. So these supporting statements up here are called premises. And so the argument is deductive because that was absolutely certain. You were able to say that's true, and that's true. So we have deductive reasoning happening right there. All right, let's take a look at an example of inductive. If you remember, inductive means it's probably true. So here we have example number 2. It says a meteorologist studied weather patterns for the last 10 years in his city. Based on his trends, he predicts a high of 25 degrees in January. So obviously something could happen and it cannot end up being true, but your inductive reasoning is what you're using here to prove that it's probably true. So it says the conclusion may be probable, but it's not certain, so that's why you're going to call this one inductive. All right, so this is the inductive argument in example 2 appeals to a pattern or a trend. So I have it highlighted right here. That's what we call an appeal to tendency. There's a tendency for this to happen, so that's what we're appealing to. It's what you're relying on for your argument. So it says this is statistical. Statistics is an important branch of mathematics, but it's very different from geometry. In geometry, you will use only deductive proof so that the truth is certain. Okay. Down here it says in a reasoned argument, the supporting statements are called premises. I mentioned that a minute ago. And the statements that are the statement that they support is the conclusion, basically the ending. If the connection between the premises and conclusion is logically correct, it is valid. That's going to come down here in a definition. True premises and valid reasoning results in a true conclusion, and then we're going to call those arguments sound. So here they are in the definition box. It says an argument is valid if the reasoning is logical all the way through, from premises down to the conclusion, if it proceeds logically. So you're going to end up seeing that you could make a logical argument that isn't even true, but logically it would make sense. You would say that's valid. But if you want to get into a sound argument, it has to be logical from front to back, from start to finish, but also your premises have to be true. So let's just take a look at the example number 3 that they're giving us. It says analyze this argument. It says, is it deductive or inductive? So we're going to be asking ourselves, is it certain or probably true? We're also going to have to identify the premises and the conclusion. Then we're going to have to say, is the conclusion valid, which means is it logical? And then is it sound? Is it true and logical? That's what we're asking for all these. So we have statement number 1 is an if-then statement. So if a man is saved, then he is a Christian. So if, then. Now, if a man is a Christian, then he should display the fruits of the Spirit. So you can see that this part's going to be, let's call it a P statement, Q, and then we're going to start again with the Q. If Q, then we'll say R. So we have this therefore down here. Therefore, if a man is saved, then he should display the fruits of the Spirit. You're following the trail here. That's like the transitive. It looks like the transitive property. But it is just going logically straight down. So let's talk about what it is. It's deductive. That was an absolutely certain, not probably. All right, we have our Bible here. That's absolute truth. That's where our information's coming from. So it says the first two statements are the premises. So you can see that they're asking you to identify premises and conclusion. So here's the two premises, and then the bottom one's the conclusion. It's valid since the reasoning is good. It made sense. We walked through it. Everything made sense. And then we're going to go ahead and say it's sound because it was valid and these were true. So we have sound. So anyhow, read through that, study it if you need a little bit more time on there. And then let's go ahead and take a look at the next page, which has it in symbols. So symbolic logic can help you analyze complicated arguments. For example, I just kind of hit on this earlier. If you said a man is saved is statement P, a man is a Christian, statement Q, a man should display the fruits of the Spirit, statement R. So you could do if P then Q, if Q then R, and then if P then R would result. So anyhow, this is a little, in summary, truth deals with statements. So a statement can be either true or false, but validity deals with reasoning or logic, okay? And it does tell us that soundness requires both. Let's take a look at example number 4. It says all of the animals at the San Diego Zoo are zebras. First of all, if you've ever been to the zoo, you know they're not all zebras. So just keep that in mind. All right, all zebras eat marshmallows. I don't think that's true either, but let's keep going. So if all animals at the San Diego Zoo are zebras and all zebras eat marshmallows, then all of the animals at the San Diego Zoo eat marshmallows. Let's start with what they say. Both premises are false, okay? If your premises are false, you don't have a sound argument, okay? Because sound had to be true premises and it had to be valid, logical. But let's just take the reasoning here, okay? The logic. If this was a true statement, if all the animals at the San Diego Zoo were zebras and all zebras ate marshmallows, then all the animals would eat marshmallows. That's actually logical. It's not true, but it follows a logical pattern. So it says this is valid because it made sense. It made good reasoning anyway. So this is a valid argument that results in a false conclusion. So you got to know the difference between valid. You just kind of want to assign that thing to good reasoning or logic. But soundness has to have truth in it. Okay. All right, so we're going to keep reading. It says you can show that the conclusion is false by giving a counter example. It says a counter example, if you don't know what that is a specific instance that fits the hypothesis but not the conclusion. In the conclusion above, a lion would be a good example. A lion is an animal at the San Diego Zoo, but lions do not eat marshmallows. So, anyhow, although the counterexample can disprove a statement, one must be careful when he cannot find a counterexample. Okay, lack of counterexample is the full phrase, is evidence that a statement may be true. So, if you can't find a situation where the hypothesis or the premises are false, you're like, I wonder if that's true. Let me try to think of an instance where it's not true. That means you're trying to think of a counterexample. You're trying to think. If you can't come up with one, that doesn't automatically mean that it's true. Because what it says right here, you may think of a counterexample tomorrow even though you couldn't think of one today. So there's that. Let's keep looking. It says, because we will focus on deductive proof, only 2 inductive types have been discussed. Appeals to tendency, because of their statistical premises, there we go, and lack of counterexample, because of the use of counterexamples in mathematics. The other 4 types of appeals involve appeals to authority, experience, analogy, and utility. In the study of reasoning, you must be aware that validity and truth are 2 different things. Remember, validity, is logical reasoning from start to finish, and truth is, you know what truth is. They're 2 different things. An argument that is valid can result in a false conclusion, and an argument that's invalid can have a true conclusion. So you must be able to distinguish valid arguments from true conclusions. And I will say that even though we're going to study a whole section on this right here, this is basically the only section that we're going to study inductive and deductive proofs. We are going to label some things further in our studies as deductive reasoning, but we're pretty much going to be done with inductive after this section. And hopefully you don't get overwhelmed by a lot of new information. Work your way through this particular section and then worry about the rest as it comes. Don't be paranoid that this is how it's going to be forever. So let's keep going. It says, if a conclusion of an argument is false, but the reasoning is valid, the argument is not sound, and you automatically know that one of your premises is false. So let's take a look at this one. Example number 5. Pigs are dirty animals. I believe that's true. Cows provide milk. True. Okay, so we're like, oh, this is true, this is true. Maybe we have a sound argument here. Therefore, rural areas have a low population density. So we have, that's also true. So we have 3 true statements here, 2 true premises, 1 true conclusion. But let's check the validity. If you remember, validity means, is it reasoning logically from front to back? So these 2 things don't seem to have anything to do with each other. And then having a low population density wouldn't come from these 2 ideas. So let's read what it says. The conclusion in this example is true. Yes, it's true. And the 2 premises are true. But the argument is invalid. There's no logical connection here. No logical connection between the premises and the conclusion. Since it's invalid, though, it's also unsound. Sound needs validity and truth. All right. This is a good example of getting a true conclusion for the wrong reasons. It totally happens sometimes. Sometimes you end up with the true answer or the true conclusion, but you weren't very good at getting there. It's kind of like an accident. It says every invalid argument contains a fallacy. So let's think about what invalid means. Invalid is good reasoning. So that means a fallacy is something that is stated that really doesn't make any sense. It's not logical. And every unsound argument must either contain a logical fallacy or a false premise. All right, let's go with several fallacies are common in mathematical proofs. Here's one, hasty generalization. It occurs when you jump to conclusions. Okay, it's based on insufficient evidence. Be sure to justify each step carefully. All right, here's another one. A circular argument is also called begging the question. You can't assume what you're trying to prove. You're trying to get there. Don't use your conclusion as one of your premises. That's what that means. All right. The fallacy of an accident occurs when you misapply a general principle to a situation for which it's not intended. So this is a good one. It says, for example, measurement is a useful principle, but it's not intended to apply to a sketch. The size of any angle may be accidental. You must not assume that angle ABC in the diagram below is a right angle just because it looks like one. You cannot call it a right angle unless it is in fact part of the given information. They'll probably give that to you by a symbol. So that happens a lot, I would say, with right angles. It looks like one. You really want to use it as one. Unless they tell you in the given information that angle ABC is a right angle, just because it looks like one, you can't assume it. And then it might put the little symbol right here. If they do that, that is considered a given piece of information. The last bit for this section is just this truth. It's not even a truth table, but it is a table. It's a summary of soundness, validity. So you can just see, you could follow it along. If your premises are true, valid reasoning, you get a sound argument. So you could study that there, and that's the little intro to section 5.5. I think that should be enough for you to work through the section, and I'll get another video up for 5.6.